Okay, here we go. Hopefully this will be the first in a series of instructional videos on how to use ANSYS for a variety of problems. As I do these, it is expected that the user or the viewer of this video has got some modicum of understanding of what the stiffness method is, i.e. F is equal to Kx, Hooke's law, and that we're essentially using the stiffness method to solve these problems. Things like LimPro use the stiffness method, ANSYS to find an element package, so it's a little bit like using a sledgehammer to crack a walnut with this particular example, but it's probably not a bad place to start, so that I can just show you around the menus how to look at this sort of particular problem we've got here. We can see we've got a 3-span beam. It has different rigidities for each of the spans. It's fixed ended, here and here, left and right hand end. You can see we've got two different distributed loads, 15 kilonewtons per meter, 30 kilonewtons per meter, 60 kilonewton point load in the end span. The 3 spans are identical. I think it's quite illogical there. So as we go down, you can see the section properties. Now I've pre-prepared these. These section properties will work to give you the right rigidity EI for each of your spans. You can see we've got a constant E there, akin to something like concrete, and you've got Poisson's ratio 0.3. That's not really going to make too much difference to us in this particular video. Okay. So what I'm going to do now is I'm going to start ANSYS. Now, we have something similar down here. I'm not going to go to Workbench or Product Launcher. I've got ANSYS CD10, which is very, very cut down 1,000 node, 1,000 element limited version. But I'm going to go straight to ANSYS, and up it comes. I'll end up with a menu, which is something like this. If you're using anything up to sort of about, I think it's version 11, no, sorry, version 13. Then you'll probably be able to use the menu like this. 14 and 15, they still have this menu present, but sort of the elements are a little bit different. So I'd recommend using 11, 12, 13 probably at the moment. Okay. So we need to start somewhere. Let's go and have a look at our menus here. You can see this is the graphics area. This is where all of your stuff is going to appear as you make it, which is good, so we can see whether we've gone wrong or right as we make it. In this menu, the ANSYS main menu on the left hand side, you'll see a number of areas. We will be going into these menus, and then there will be sub-menus. They're different colours, as we'll see in a minute, so that helps us a little bit. But essentially, we've got to build the model, preprocessor. That's generally where we'll be. Then, after we've built our model, we'll go into solution, where we'll apply loads and boundary conditions. We'll also solve it there, and then we'll go into the general post-processor afterwards, read the results of ANSYS' database, and then we'll be able to see what's actually going on. Some of the results, plot things like bending moment diagrams for this particular problem. Okay. So I'm going to use the method of direct generation. There is another method called solid modeling where you make volumes and areas and lines up, but the problem with that is it's overkill for what we need. To actually be able to create nodes and elements in space exactly where I want them, I might as well directly generate them. So this is the way I'm going to go with this particular model. Okay. So first of all, I'm going to enter the preprocessor. Oh, I will talk about some of these menu options up here, but I'll use these now and again. We've got plot controls, and we've got nodes and elements, things like that. We can control numbering, all sorts of things like that. It's a bit more of like a typical Windows menu. And actually up here, where this cursor's blinking, we can put ANSYS commands. Every command that or click that I make issues an ANSYS command, and it has an equivalent typed command structure to it, so I can actually type in this little box here and the same thing will happen. But of course that comes with experience. You've got to learn what the commands and bits and pieces are. So I'm going to use the graphical user interface and pick and click these. So preprocessor, Okay. What I think I might do actually is enter a title. So if I go File, Change Title, it comes here. So this is issuing the slash title command. I'll type 3 span B. Okay. Now nothing appears only until I've started creating nodes and elements will I get a title appear. So that's just for my reference later on. Now, element type. I'm going to click on where it says element type here, and a little red menu comes up. Add, edit, delete. At the moment, we've got no element types defined. So what I'm going to do is I'm now going to add. Look, see, I've got all these different elements that I can choose from up here: beam, link elements, pipes, solid shells, all that kind of thing. Ours is going to be quite simple. I want a beam element. Now, as you look at this, you can see it tells you what the element is here on the right hand side, but also it's got a number associated with it. That's ANSYS's own element library number. Nothing to concern ourselves with. It's this number here, this element type reference number, which will be unique to our model. So as this is the first element, it's trying to call it element reference number 1 for our model. Now, I want to select beam, 2D model, so I want 2D elastic 3. Okay? So I'm now going to click on OK. Done. Now I can select various options. This is what we call key options. So if I click on options, just so that I can show you what's going on. But you've got member force plus moment output. What normally happens is that you can access data from the in the global system, essentially. So whatever I get out in terms of moments, rotations, displacements, etc., 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 is all relative to this little Cartesian triad you see in the background. So it's a global coordinate system. What happens if I've got a member that's orientated at some angle to the X, Y, and Z system? Well, we might want to get member forces. In other words, actually look at forces which are relative to its own local axis. So that is possible to get that. So I can click on this and go include or exclude output. For this model, it doesn't matter. Our beams line up with the global x-axis. So that's fine. We can carry on as it were. But I just wanted to show you that elements do have key options here. Okay. Let's close that down. So I've chosen an element type. Next thing I need to do is give it some geometric cross-section properties. This is not a volume element that we're going to use where I can just sort of define it by a number of nodes and it knows what geometric space it occupies. I actually got to tell it things like the area, cross-section area of our beam, supplement area, etc. So I'm going to click on real constants now, and I'm going to go again to add, edit, delete. And here you can see at the moment there are none defined. I clicked on add there. It went to beam 3 because it's the only element type I can add real constants for. So I'll click on OK. And I'd like to define the properties for my first span. So this is real constant set number 1. It'll have a cross-sectional area. Let me get that right. Now I'm gonna work in meters. I've not really said much about units at the moment, but really, if you're doing it really for the purpose of dynamics, I would stick to things like newtons, meters, seconds, and kilograms. You can choose whatever units you like, but as long as the numbers are compatible with your material properties, etc., then you won't go wrong. But it's the biggest point of error that people start to enter different units into different parts of ANSYS, and you have a problem. But I'm going to stick with meters here, so I'm going to go 0.06 for the area for the first span. Its second moment of area, 4.5 e to the minus 4. Okay. Now you can do that. That really means 4.5 times 10 to the power of minus 4 if you write it like that. The height, 0.3. Like that. Okay. We don't have to worry about shear, deflection, or strain here. This added mass per unit length. This is quite useful if you want to stick a mass on your beam that's, say, distributed along its length. You can apply G later on in terms of acceleration, and then you can do like a self-weight analysis. So let's click on OK now. I need more real constant sets now. That's only the first span, so I'm going to go add for beam 3, click on OK, and this is now real constant set 2. This is going to be for my second span, so I'm going to go 0.0866 for the area. IZZ is 13.4 e to the minus 4. And then we've got the height 0.433. See, two single constant sets. I want to add another one for the last span that's got a different rigidity. So the area there is 0.0756. IZZ is 9e to the minus 4. Okay, and the height there 0.378. Okay. So, okay, all that looks okay. Done. Let's close that out. So I've now got my real constants sorted, ready for input in the various spans. Material properties next. Click on material properties, and you can see there's another menu down here, there's some sort of interesting things. We want material models, so click on material models, and up comes this window. So for material number 1, we want to define some structural properties. So there it is, second one down, structural. They are linear, it's a linear problem. They are elastic, isotropic. If I put things like a Young's modulus in, I can have different Young's moduluses in different directions if I want to, so orthotropic properties, that kind of thing. But I want isotropic, so isotropic, and there, I can put in my Young's modulus in the x direction. So that will be, let's have a look, 2e to the 10, because I'm dealing in newtons and meters. That's newtons per millimetre squared. I'll let you think about the units for that, so hopefully that should be okay. Poisson's ratio 0.3. Gone. Okay. Right. So done. And we can exit this, so we go material, exit. Okay. So now we're down to modelling this thing. Now, beam elements don't suffer from what we call mesh refinement. So in theory, I could model 1, 2, 3 beam elements for each of the spans. But having said that, for plotting things like bending moment diagrams and outputting various moment results along spans, it's best to have a few nodes along a beam for those purposes. So in this instance, because each beam is 4 meters long, I'm going to choose every half a meter to have a node. So that means I need 8 elements every 0.5 of a meter long in each of the spans. So 8 with 3 spans, 3 x is 24 elements. So if I've got 24 elements, that means I need one more node than I have elements, because the elements connect between nodes. Okay? So that's my philosophy here relative to the model that we're inputting. So I'm going to start now by defining nodes, first of all, and then I'm going to copy. There are various ways of doing this. This is one of a number of ways, but we've got to start somewhere. So modeling, create nodes in active CS. So node number 1 goes at 0, 0, 0. Look, it's blank anyway. You could just go on OK, but it's probably good practice for me to put that in 0, 0, 0. Now, you see the title has come up, three-span beam. There is actually a node at the triad origin there. The trouble is you can't see it because it's been obscured by that. But trust me, it's there. It's probably got a little number associated with it. All right. Okay, so I need to copy that 25 times. So there we are, the copy command there. So copy, nodes, copy. Up comes this nice little pick box. So I'm going to pick that. Window OK. Total number of copies, including the original. Okay, so I need 25 sets of nodes, including the original. So that should be 25 in there. Each node, as I generate it, will go along 0.5 units in the x direction. So let's get 0.5. Node number increment, well, 1 becomes 2, 2 becomes 3, 3 becomes 4. So it's ANSYS has intelligently set that, but I wouldn't always take that as gospel. Check that every time you do it. So if I click on OK, I've now got 25 nodes. Right. So what I need to do now is I need to generate some elements. So first thing we're going to do is go create. Look down here in this green menu, you'll see elements, and I'm going to look at element attributes. This box comes up. Now what we need to do is we need to set what element type I'm about to generate, what material number I want associated with that element, and what real constant set number I want associated with that element. Now look, these drop down boxes are such that I've only got one element, so I'm going to have one material type, but I defined 3 different constant sets. So in actual fact, what I'm going to do is I'm just going to generate the first span, copy filters. I'm going to put an element between 1 and 2, then I'm going to copy it. Then I'm going to put an element between, it's probably node 9 and 10, copy that along, and then probably between 17 and 18 and copy that along. But I'm going to change the real constant set each time to ensure that I get the right section properties. Anyway, for now, I'll click on OK. That's alright. So I go auto numbered through nodes. So I'm going to click on 1 to 2 and then go OK. See a little blue element there. Good. I'm going to copy that. Copy down here to the elements. So click on that. Auto numbered. There it is. Here it goes orange when I've selected it. That's good. In actual fact, if you want to deselect, press the right mouse key and the arrow comes up and deselect it. Press the right arrow key again. Arrow points upwards. Press the left key. Select. You'll get used to that quite quickly. So I want to copy that. I picked it, click on OK. Number of times I want to copy it. Well, there's 8 elements in the first span, so I should need to change that to 8. Oops, 28, 8. I also want to include the original. Node number increment is 1. Okay, so let's click on OK. Up it goes, right? Okay, so next I want to create elements, but now I need to change the element attributes because the real constant set I'm associating with the second span with real constant set 2, so I click on 2, go OK, and now I've changed those attributes, hopefully to the right one. So if I go now, modeling, create elements auto numbered through nodes, 9 to 10, okay. Then go copy, elements auto numbered, 9 to 10 there. Click on OK. Total number of copies, or on 8 copies of those, with a node number increment of 1, of course. Click on OK. There we go through again. That's node 17. Right. Quickly go through this then. Create elements, element attributes. I need to set the real constant set to 3 now. Click on OK. I now need to create elements auto numbered through nodes from 17 to 18. Okay. There, that one. Copy elements auto numbered. That one. Click on OK. Again, 8 copies, node number increment. Right. So there is the whole being done. That's really the pre-processing over, apart from the boundary conditions and loads, which you have to put in the solution phase. So we're going to do that next. Right. So let's close down the pre-processor and then go to the solution phase and say we need to define loads here. Now, before I do that, actually, let's just have a quick look at analysis type. You can see you've got something called new analyses. This just shows you the sorts of things that ANSYS can do. The buckling analysis, transient, mobile, static. Where static, it's always the default, so you don't have to go for that every time if you're just knocking up a quick static model. So anyway, define loads, apply, structural displacement on nodes. Now look, I need node 1 and node 25 completely fixed in vertical, horizontal and rotational degrees of freedom. So I'm going to select 1 and 25 and then go OK. And look, I have a command that says all degrees of freedom, so I might as well do that. Yeah. UX, UY, the translational, and you can see rotational there. I can select individual degrees of freedom if I want to. So I'm going to click on all degrees of freedom, type 0 in there for the value. Now I need some support, so I think at node 9 and node 17. So structural displacement on nodes, so at node 9 and node 17 there, click on those. I click on OK, and look, the default comes up that I clicked last time, which was all degrees of freedom. Make sure you click off of that, so it's all blank, and you want to put, what UI in, don't you, I guess, so click on UI, value of 0. They're quite intuitive. You get these little blue arrows to show translational boundary conditions, and you get little orange-headed arrows which are coming out the page at you. So they look like little orange crosses to show the rotational zone. So you always know when a boundary condition is present. Loads of it. So what I'm going to do is I'm going to say define structural. Let's put down that menu. Look, there's pressure. That sounds like a good one. So pressure. On beams, I wouldn't use on elements for this. On beams is a much easier command to use in these circumstances. So if I go on beams, I'll tell you what, I'm just going to go through and click all of these here because I'm just picking them. Okay. And go OK. And now it says, what side do I want to put the pressure on? These beams, I think, have got something like 6 sides you can put axial pressure on. Luckily, the load key that we want, the side that we want to put this on, is side number 1. So look, value pressure at node I. This was the span with 15 kilonewtons per meter on it. The meters is okay, the kilonewtons isn't. Need to get that in newtons, so that's 15,000. 15,000. Okay. So if I click on OK, you've got this pressure. We'll do it again for the central beam, so on beams, select all of those, like so, and we want 30,000 this time. Okay, again on edge number 1, load key number 1, click on OK. Right, okay, it hasn't graphically distinguished that that's a different load at the moment. Don't worry about that, that's not really an issue. It's got a distributed load on, it is different. Right, next I want to apply a structural force moment on nodes. This is another good reason for having nodes intermediate in your beams, as it were, because you can only apply forces where there are nodes. Okay, so force displacement on nodes. There's pick box, I think it's probably node 21 we want there. Y is vertical, so I want a force in the Y direction, so that's Fy. The value, well, it acts downwards, so it's negative, minus 60 kilonewtons, so 60,000 newtons. So click on OK. Graphically, that looks alright for us, doesn't it? Okay. How do I know I've put the right section properties in, that kind of thing? I can do something to actually show me the real constants on this, because in the real constants, put the height of the beam. So if I go plot controls, style, size and shape, what you'll see here is, you'll see, do you want to display the element? This is this E shape command, so to say, yes please. And then I can scale the real constants, so I can make things bigger or smaller, so I can see them. It's just an investigative tool. It is actually quite useful. So if I put 1 so that I get them actual size, and then I go, okay, right, okay. Things have disappeared for the minute, it always does. This is just a graphical issue with ANSYS. If I want to get elements back, I'll just go plot elements. There they are. They're on there. Okay. See, smaller, bigger, It only remains for me to solve this now, so this is actually the easy bit. So if I go solve, current LS, that's for current load step. There's all sorts of non-linear things that ANSYS can do, which we're not going to worry about at the moment, because we have different load steps. We only have one load step. It says, should I solve? Please, yes, okay. Little circle thing around, and should quite quickly say solution done. Great. Close. File. Close. So, that having been said, we now come out of the solution phase and we go into the general post-processor. Let me have a look at where it says results summary. So I'll click on there and it says this is the data set that you have on your results file. You have to read in data sets. You might have a list of those. If you're doing an earthquake time history analysis, you might have that in a list. So it could be, you just want to select what's happening at a particular time or something. But we've only got one, so let's just close that. I'm going to go read results, first set. There's only one set there, so read results, first set. See the little thing went round for a bit? Nothing's happened, but nothing is supposed to happen yet until I start saying cannot plot result or have a look. So if I now go plot results, deformed shape, I'll plot the deformed shape and the undeformed, I think. So we'll get both in the same graph, and there you go. So you can see maximum displacement probably looks like it's in the mid-span there, about 1.3 millimeters, because that's meters, isn't it? Okay, that makes sense. Okay, you can't see boundary conditions and things on there. If you want to put boundary conditions on, you go plot controls, style, oh sorry, apologies, symbols, okay? But you can select all kinds of various bits and pieces here, reactions, apply to boundary conditions. I think if I select that, you can now see. Don't worry about the purple arrows. This is even putting reaction forces on and trying to work out what the magnitude of those are. Do not worry about those. We'll just leave them there. Okay. What about moments? Well, we'll probably be interested in moments that this supports, the end supports, that kind of thing. You'll have bending moments there. How would I get them out? Well, one way is to list results. List results. Just clicked on that. Element solution. And under here, have a look, scroll down, it's structural moments, that's a good one. And I can have X, Y, and Z. Now think about this logically. Z is the axis coming out of the page, so it's moments about that axis I'd like. I'll click on that one and go OK. Now, so it tells you the element, it's connected between node 1 and 2, and it tells you the moments at nodes 1 and 2. So look, you've got 16.746 there, kilonewton meters. Let's have a look at node number 9, because that's the first internal support. 26.5, 1 kilonewton meters. Probably about node 17, 37.9 kilonewton meters. And it's right at the end, we've got 26.04 kilonewton meters. Okay, great. So we've got the physical numbers, and we can see what the bending moment diagram is doing from the numbers in between all the different nodes. But we'd probably like to plot that as a bending moment diagram. So, how do we do that? Well, it's not as straightforward as just pressing a button like you would do in something like LimFi, and it come up and just show bending moment diagram. It doesn't intuitively know that we want to see that. So, bending moments actually reside on the file, the database file behind, and only if you extract them into something called an element table can we see them. And it just so happens that the moments at, let's have a look, think of it this way. Each element has two nodes, I and J. So its lower numbered node is I, its higher numbered node is J. What we want to do is, we want to get the moments out for nodes I and J. And the moment at node I resides in a little library accession place called a miscellaneous item number 6. The moment for the node at nj resides at miscellaneous item location number 12. So this is how we can plot bending moment diagrams. Let's first of all, we need to find something called element table down here. So there it is, element table. Click on it and go define table. At the moment it said there's no data defined in this element table, so I've got to add some data to it. So go add. Label, use a label for item. Don't worry about this first box, that's nothing. Use a label for item. I'm going to put I moment, alright? Because I want the first data to be the moment at node's I. So if I go down this box here, scroll this little box here, by sequence number, that's what I want. So I'm going to click on that. It's called MISC, so it's a miscellaneous sequence number item. And it's number 6 I want there. Okay, so after the comma, put 6 and go, okay, here it comes. So I moment is going to extract miscellaneous item number 6 from the database. We're going to add. This one's going to be J moment, and go down the bottom there by sequence number. And this is going to be item 12. 12 after the comma. Okay, so done. Close that down now, and then what I'm going to do is now go up to where it says plot results, because I want to plot this bending moment diagram, and it will reside under contour plots, the actual one that you want here. So if you click on contour plots, you can plot all sorts of bits and pieces of data. So the best way to do this is then go to line element results and look and saying, what would you like to plot at node I? I'd like the moment at node I, if that's right, please. Thank you. What would you like to plot at node J? Well, at the moment it's got I moment. So if you plot the drop down menu, change it to J. Now you've got an additional scale factor. In civil engineers, we like to see positive bending moments acting downwards. So I bet that if I plot this up, it will actually look the opposite way around to what I want. Okay, so I'll do that first. There we are. Bending moment diagram. Typical UDLs, but it's just the other way around to what we'd expect. So if I do that again, I put -1 in there. It's the right way around now. Okay. So you can see you've got a bending moment diagram there. Okay. So I might want to write a report for Weeksy with this little bending moment diagram in there. If I'm using a lot of black ink in my cartridge because I want to print it out, that's not a good idea in that nasty black background. So if I want to change that, I can go to plot controls, style, colors, reverse video. There we go. So white, black, change that. I'll change it back. I'll say for one minute. So style, colors, reverse video. Let's take it off. I might want to output that. So as a hard copy to a BMP file or a JPEG. So I'll go plot controls, hard copy to file. Okay. So maybe I want to save it as a JPEG. Here I can change the file name. That's okay. Already there's a little box called reverse video ticked. So if that's black, when it outputs it to the file, that will become a white background. So you don't have to change. If you're quite happy looking at that on the screen, no problem at all. Okay. So done. That will now printed that file. I'm not going to show it to you, but it will have done that. Saving file, save as. Now, ANSYS would like to save it as a .dv file. That's a database file. So I'll save it as something like 3 span tests. Okay, that's now my database file. I'll click on OK. Alright, now I can always resume from that. I can go File, Resume From, and then pick up. You can see, look, I've saved lots and lots of databases from models that I made there. So I can go 3 span test, click on that, resume. I won't do it, it's already in, but that's how you do it. It also saves something called a database backup. You can see, look, there's beantest.dbb. So in actual fact, there is a fail-safe there. But let's just say you've screwed up and you've got a corrupt model. Got to make it. Go File and go List, the log file. Like it. There's this great big ANSYS log file where all the commands that you entered during your time playing around with this program are there. Look, I moment, J moment, S moment. It records everything. So in actual fact, let's go see if I can find out where I started this model. It'll probably be where I put the title in. But slash title is then B. Probably, if I strip this out, without, yeah, file. I'd have to save it first. Okay, so I'll probably do this in a different video where I show you this. But save as, strip it out in a text file, save that text file, read input from. That wants to read a series of ANSYS commands. And the beauty about doing it this way is it's independent of version number. So if I'd made a model in ANSYS 11 and I want to use ANSYS 10ED, it won't read in the database, but it will read in a log file. Okay? Anyway, I'll hopefully make a few more of these, and hopefully that one's made sense and will get you going on this span B and get you toiling around with ANSYS at the start. Okay, so cheerio.